Hey, this is Mr. Beckstrom, and today I wanted to take a look at an example from section 5.8. This is exponential growth and decay models. So here's the problem, and it says, after the release of radioactive material into the atmosphere from a nuclear power plant in a country in 1995, the hay in that country was contaminated by a radioactive isotope with a half-life of 6 days. If it is safe to feed the hay to cows when 15% of the radioactive isotope remains, how long did the farmers need to wait to use this hay? Alright, so we're going to have a decay problem, and in those, we're going to use this little formula here that says the remaining amount with respect to time is equal to the initial amount of that. In this case, it's a radioactive isotope times E to the K, which is a constant that we'll get in order to, it's directly related to half-life, times T, which is the amount of time it takes to decay. All right, so remember we said this is the amount remaining, and this is the initial amount, and this is E. We just did a quiz for E, so hopefully you kind of a little bit better understand what that is, but it just represents an irrational number, 2.718. It goes on forever. And then K is our constant and T is our time. So I can rewrite this. So if first things I want to do is I need to find this K constant. That's very often that's the first thing we're going to need to do because it's not going to give that to us. So what we can do here is we know that if our initial amount is, say, 1 of these radioactive isotopes, then after 6 days, that's our T there, we're just going to have half of that left because that's what half-life means. Half-life of 6 days. So in 6 days, I'm going to write that K, in 6 days, we're going to have, if we start with 1, we'll have half left. You could start with 2 and then have 1 left. You could start with 10 and have 5 left. We're all going to get the same fraction of 1/2 over here, regardless of what 2 numbers we start with, because we're always starting with half of whatever we have over there from over there. All right, so I'm just going to I'm going to write 1/2 is 0.5 is equal to E, and we usually put the number in front of the variable there. So this is what we're trying to solve. We're trying to solve for K. That's our unknown. So I can take the natural log of both sides. So natural log of 0.5 is equal to the natural log, oops, the natural log of E to the 6K. And this is something we can do. We can take the natural log of both sides. So we're still going to have the natural log of 0.5.
Yeah, she's still sleeping.
And this is going to be equal to the natural log and E. Remember, they're inverse functions of each other, so they kind of cancel each other out. So if we have the natural log of E to something, we just get that something back, 6K. And finally, we're going to divide both sides by 6. So our constant is going to equal to the natural log of 0.5 over 6. Now at this point I'm going to put this into my calculator, see if it gives me a nice number, which I'm not sure if it will yet, but if it doesn't, I'll just leave it like that. So this is a natural log of 0.5 divided by 6. And here, yeah, no, we're gonna get, it looks like some irrational number here. So I am just going to actually, for my calculator, I'm going to store that, hit the store as X. So now if I need to use it in my calculator, I can just put X instead of that big long number. All right, so now that we have our K, now we can solve this problem right here. So I'm going to do the same kind of thing. So it says, if it is safe to feed the hay to cows when 15% of our radioactive isotope remains, how long did the farmers need to wait? So now we're going to be solving for the time. So that's going to be our variable. So I'm going to set this up the same way. So the amount remaining, if I started with 1, would be 0.15 because that's 15% of 1. So 0.15 is equal to 1 e to the kt. Now I'm going to leave this number as just, or this value as k. We know that k has a value, but it just saves me a little bit of space, and I'll put it in at the end here. Alright, so we got that. So once again, I'm going to multiply or apply the natural log to both sides. So natural log of 0.15, put a parentheses around that, make it a little bit neater, is equal to the natural log of e to the kt. Alright, once again, natural log of 0.15 is equal to, these are inverse functions of each other, so they cancel out, just leaving me the kt, and now remember we have a value for that k, so I'm going to divide both sides by k, so t is equal to natural log of 0.15 all divided by k, and I'm going to go ahead and write what k is now, all over the natural log of 0.5 over 6. And remember, I stored this whole thing on the bottom as x in my calculator. So now when I go to get my final answer, I am just going to do natural log of 0.15. So natural log of 0.15. And that's going to be divided by, and in this case, I saved that last answer as x. So I'll do that. It looks like 16.42. So about 16.5 days it'll take in order for this isotope, radioactive isotope, to get down to 15% with a 6-day half-life. All right. If you have any questions, let me know, and I hope you have a great rest of your day. Thanks.